Okay. Well, I think we better switch over now. So I think we have our next presentation, which is from Jonathan Rizzo, who is looking at designing a VLF board for the Tangerine, a leaf board.
Hi, my name is Jonathan Rizzo, KC3EEY. I'm a VLF natural radio enthusiast and senior electrical engineering student at the University of Scranton. I'm currently designing a VLF module for the TangerineSDR for automated reception of natural radio emissions and amateur transmissions in the ULF and VLF bands. For more detailed background on VLF natural radio and the motivation behind this module, I invite you to view my TAPR DCC 2019 presentation, Ground-Based Observation of Whistler Waves, on the Ham Radio 2.0 YouTube channel. For an example of a Raspberry Pi-based VLF automated reception system, I also invite you to view my HamSci 2020 presentation using a PVC pipe antenna and a Raspberry Pi to detect VLF natural radio on the Ham Radio 2.0 YouTube channel. The random nature of VLF natural radio occurrences and how sporadic they can be, especially chorus emissions, it really isn't practical for the listener with a portable VLF receiver to listen for them unless substantial time and effort is put forth to catch them. Natural radio emissions often occur at inconvenient times, like in the early morning or during bad local weather conditions. I used my portable VLF receiver quite often and didn't hear a single whistler. This doesn't mean these events don't occur, you just have to be at the right time and the right place on Earth. Another issue is power line interference. 60 Hz hum and its harmonics are radiated from power line conductors all the time, often changing in harmonic content as electrical loads like motors and switch mode power supplies dump their harmonic byproducts back onto the power lines. Power line emissions can radiate for miles and still wash out even the strongest natural radio emissions. A great solution to the limitations and pitfalls of live listening is an automated VLF reception system. E-field receivers are sensitive to the electric component of the wave, and B-field receivers are sensitive to the magnetic component. Both offer different advantages to the VLF enthusiast and researcher, and automated systems often contain both, but either one can be used in a single receiver system. These receivers are installed outside, most of the time in a sealed enclosure and mounted on a mast along with their antenna, and are powered by a battery, sealed lead acid is best, or isolated DC from the feed line. Current draw is usually very little, so a sealed lead acid battery of a few amp hours can last for months. Isolated DC to DC converters can be used as well, but care must be taken so that their switching frequency is high enough that it does not cause interference in the VLF band. VLF audio and sometimes DC power is transported on the feed line running from the VLF receivers to the data acquisition system. Unavoidable ground loops due to the voltage difference between earth ground and data acquisition ground can cause mains hum injection into the receiver front ends via their ground. So audio isolation transformers and isolated DC to DC converters are required. Automated VLF reception systems include the receivers and associated antennas, as well as the data acquisition system that provides the automation. The receivers can either be E-field or B-field receivers, and these systems utilize one E-field and two B-field receivers for triple axis reception that allows for varying and distance calculations of incoming signals. E-field receivers consist of a high impedance front end, either a JFET or op-amp circuit with some added gain, used as an impedance converter. The gate resistor of the JFET sets the input impedance, usually 10 megohms or higher. The antenna is connected directly to the gate of the JFET or input to the op-amp, usually with an inline choke. The output of the front end is much lower impedance and is often filtered, then applied to an audio gain stage for headphone monitoring or a feedline driver to drive a long length of cable back to the data acquisition system. The antenna is a simple electric field probe connected directly to the input stage, and coax cable cannot be used due to an impedance mismatch. The reason why such an electrically small antenna can be used is because of the high impedance of the input stage. If one were to use 5 kHz as the middle of the VLF natural radio band, the wavelength would be 60,000 meters. The impedance conversion is much more practical than even a quarter wavelength antenna. Here is a block diagram of a basic E-field receiver showing the probe antenna, input stage, filtering stage, and output stage, either consisting of a headphone or feedline driver. An earth ground or counterpoise is also required on the input stage, but it doesn't have to be a good ground. The counterpoise created by grounding an E-field receiver to your body is often very effective, especially in portable receivers that you hold in your hand. Another thing to keep in mind is that when connecting to a data acquisition system plugged into mains power, isolation transformers on both ends of the audio feed line are required to eliminate a ground loop, then inject 60 Hz hum into the input stage via ground. Another alternative is an amplitude-modulated audio optical link via fiber optic cable for complete galvanic isolation. Power can be provided either via battery at the receiver site or from a feed line via DC to DC converters. However, isolated DC to DC converters must be used on both ends, and their operating frequency needs to be high enough that it doesn't cause interference in the VLF band. B-field or H-field receivers consist of a loop antenna coupled to the front end via an audio isolation transformer to match impedance between the low impedance of the loop and the high impedance of the input of the op-amp circuit. After the front end, filtering is implemented and passed to an audio gain stage for headphone monitoring or a feedline driver to drive a long length of cable back to the data acquisition system. To determine the bearing and direction of incoming VLF signals, 2 orthogonal B-field loops are required for north-south and east-west bearings. VLF enthusiasts often employ orthogonal loops for stereo listening of VLF signals. The magnetic component of observed natural radio emissions often has different signal and propagation characteristics and can provide additional information than the electric component can. Whistlers and tweaks are often stronger in the B field than in the E field and provide additional signal and propagation information. B field receivers require a good ground or counterpoise connection on the input stage and feedline isolation on both ends. Here is a block diagram of a basic B field receiver showing the loop antenna, input stage, filtering stage, and output stage, either consisting of a headphone or feedline driver. An earth ground or counterpoise is required on the input stage for good receiver sensitivity. It is recommended to use shielded loops in an automated reception system because noise sources often come and go, especially with dynamic power line interference from harmonic generation originating from electric motors and switch mode power supplies. These harmonics are injected back onto the power lines and can radiate for miles. Audio isolation transformers on both ends of the audio feed line are also required, and the receiver is powered in the same way as the E-field receiver. Here is an example of an installed E-field receiver on the left. The receiver electronics are enclosed in the PVC pipe, and the feed line and ground come out the bottom, while the antenna element is inside and is in most of the length of the pipe. On the right is a B-field receiver with loop antenna. The receiver electronics are housed inside the gray enclosure, and the feed line and ground come out the bottom. The loop connects from the top. The data acquisition system captures the VLF audio and records it digitally. sometimes adding a timestamp reference to GPS time for correlation purposes. After recording and timestamping, the data is processed using digital signal processing techniques for filtering, event detection, event storage, and visualization. The simplest data acquisition system is a digital audio recorder. For the serious enthusiast, a computer with a good sound card, a GPS pulse per second signal, and appropriate software like Spectrum Labs or vlfrx-tools can be used to capture, record, filter, do event detection, and audio streaming for live listening. Professional researchers often use commercial data acquisition systems like one from National Instruments or others. They can also create custom data acquisition solutions, like the awesome VLF receiver designed by researchers at Stanford University. vlfrx-tools is an open-source VLF receiver toolkit for signal capture, analysis, and storage of VLF signals and events. It's written by Paul Nicholson, a VLF enthusiast very active in the VLF community. VLF audio and a GPS pulse per second signal is fed into the sound card of the computer. vlfrx-tools captures the VLF audio and timestamps each sample. Offset correction is applied to the timestamp so they align to GPS time. The signal is then applied to a tracking filter that tracks mains hum and removes it and its harmonics. The filtered signal is then fed into a whistler and chorus event detector that logs each event. Finding location can be accomplished with spheric time of group arrival. Bearing and distance of incoming VLF signals can be determined with triple axis reception. Sudden ionospheric disturbances can be detected with phase measurements from VLF transmitters. The source code can be compiled on VSDs in Linux, and live listening can be done via streaming to an IceCast server. This is a block diagram of the signal flow between the utility programs of vlfrx-tools, utilizing circular buffers and named pipes for transport. Audio and the pulse per second signal come in through VT card, where each sample is timestamped. Offset correction is applied through VT time. The 60 Hz hum and harmonics is removed with the tracking filter, a VT filter. The signal is then combined into a 3-channel stream with VTCAT and sent off to the event detector VT event and the time of group arrival utility for time of group arrival calculations. It is also sent to VT resample that downsamples the stream and VT Vorbis that sends it to an IceCast server for live listening. VLF audio module for the TangerineSDR will replace the sound card and use the GPS DO for timestamping. This will produce a stream with combined channels like VTCAT does and present them over a TCP socket via the data engine's Ethernet port. Any server on a local network or the internet running vlfrx-tools can accept this multi-channel stream and perform the various tasks such as event detection, sudden ionospheric disturbance detection, time of group arrival measurements, and data exchange, streaming, and signal archival, all without the need for a high-quality sound card and a computer. For the VLF audio module came from a post on the VLF Natural Radio Groups.io group with a discussion of the Behringer UMC 404HD professional USB audio interface for professional audio and music recording applications. It has 4 analog inputs and can sample at up to 192 kHz, and was discussed as a high-quality capture interface for VLF and GPS pulse per second signals. Paul Nicholson decided to try it out on his automated VLF reception system that previously employed an M-Audio 192 PCI high-quality sound card. He found it performed better or the same in much of the testing that he did, and decided to use it in production instead. It utilizes a Cirrus Logic 4272 24-bit 192 kHz stereo audio codec for analog to digital conversion with 114 dB of dynamic range. It also utilizes the AD8694, NJM2122, and RC4850 op amps for analog filtering, gain, and buffer stages. Here is the front panel. The USB port is in the back. For the VLF audio module, the CS4272 is not a good choice. Only 2 analog input channels are available. At least 3 are required for the VLF audio module, and ideally 4 for a backup receiver. It's also a codec, so that means there are analog outputs as well, which are not required and won't be utilized. So an alternative had to be found with at least 3 analog input channels and no analog outputs. Since it simplifies hardware design, a single IC solution can be used with the same performance. I chose the Cirrus Logic CS5364. It offers 4 analog inputs and no analog outputs, with a dynamic range of 114 dB. The master clock is obtained from one of the programmable clock channels on the GPSDO. Audio samples are transported via the I2S or TDM port to the data engine FPGA. I2S only supports 2 channels, and TDM can support 4. The FPGA will set the number of active channels, sampling rate, sample length, and master clock frequency based on the user configuration settings. The VLF audio module interfaces to the data engine as a leaf board. The I2S or TDM port is connected to a high-speed serial bus on the M.2 connector and I2C control via the Raspberry Pi I/O header. It may have an EEPROM for leaf board ID. For operation, the user connects the VLF audio feeds via audio isolation transformer to the appropriate screw terminals. The FPGA configures the active channels from 1 to 4, the sampling rate, sample length, and master clock configuration via I2C based on user configuration settings. It also configures the GPSDO programmable DDS channel to generate the master clock frequency required for the configuration. Samples are transported via I2S or TDM to the FPGA and are time-stamped reference to GPS time the same way VT card timestamps a sample. Because their master clock is derived from the GPSDO and the low latency of the FPGA, the timestamps do not need offset correction. The channels are combined into a stream in the same way VTCAT combines channels, and is presented to the Ethernet port via a TCP socket. The channels are combined in the same way as VTCAT combines them, and the timestamps are applied in the same way as VTCard applies them. So the stream is compatible with vlfrx-tools, and the TangerineSDR and VLF audio module can provide a high-quality VLF capture and timestamp interface in a compact network SDR. These tables are taken from the datasheet. For 192 kHz in either I2S or TDM modes, quad speed mode must be used. Depending on how the master clock divider is chosen, one must select the appropriate master clock frequency, and the serial clock and word clock are generated by the CS5364. For TDM mode, only the serial clock is generated. VLF automated reception systems are an invaluable resource for science. According to an anecdote from Paul Nicholson, written on the VLF Natural Radio Yahoo group, Dr. Robert Schofield, a physicist involved in the LIGO experiment that confirmed the existence of gravitational waves as predicted by Einstein, was tasked with verifying that terrestrial sources of noise, such as spherics, did not generate false detections in the LIGO data. Dr. Schofield contacted Paul and requested timestamp VLF data, but he did not have recorded data in his server's cache for that time period. So Paul contacted Mike Smith, a VLF enthusiast that supplies a VLF stream to Paul's servers. Mike uses a high-quality sound card sampling at 192 kHz to capture wider bandwidth than the downsampled streamed version of the data Paul had on his servers. And he had data for the time period that Dr. Schofield needed. Data was provided to Dr. Schofield. So, the VLF reception system and network from Paul and Mike played a small part in one of the biggest discoveries of physics in recent years. This is why these VLF reception systems are so important. A VLF receiver built with old answering machine parts and a TangerineSDR has the potential to do amazing things. I'd like to thank the following: the National Science Foundation for their financial support via the listed grants, Amateur Radio Digital Communications, and the University of Scranton for their financial support, Tom McDermott, N5EG, and Scotty Cowling, WA2DFI, for their technical support, Dr. Nathaniel Frizzell, W2NAF, for his endless support, motivation, and inspiration, and Paul Nicholson for his amazing support and assistance he has given me, his amazing software vlfrx-tools, and his contributions to myself, my projects, and the VLF community at large.
Thank you very much, Jonathan. That was great.
Thank you.
Let's see, do we have any questions here? Well, I think one person's asking, what about using military surplus VLF receivers? Why are we doing this?
Well, I was actually looking for a couple of those receivers because I wanted to know how they were designed and how they actually work. From my understanding, they contain a lot more stages, and they don't necessarily output an audio feed that is the whole bandwidth of the VLF band. So I would really like to get one and look at them and see if it is possible to actually use them. But for the time being, for this system, so far I've had good luck with homebrew receivers that I built.
Thanks. I think one thing is that since we're trying to build a fairly complete personal space weather station, it's really good to have these different modules where, if you want to use it for doing VLF, you can do so. If you want to use it for doing HF, you can do so. So I think this is a really nice board that will help to round out the system as a whole.
So I have a question, my own question for Jonathan. The Cirrus part that you picked, the 5364, can you give us a little more info on that? Is that a quad channel part, or are you going to use multiple ones, or what does the performance look like?
Well, so the 5364 is quad channel, and its dynamic range is 114 dB, and it is specifically an A to D converter, so it doesn't have any outputs, and that's why that I chose that part, because I didn't want to have extra A to D converters, even though that I could have. I figured this would simplify design, and it would give pretty good performance. That's why that I chose this one.
Jonathan, do you know if there's an easy way to calibrate an LF-VLF H-field antenna system to actual field strength?
Yes. So when I was doing my senior project, I built up a VLF receiver designed by Paul that has, so what he uses is an AC line filter choke as a transformer to inject a calibration signal to the input of the receiver. And he uses a calibrated, he uses a calibration signal that's synced to GPS. Unfortunately, he hasn't released a lot of documentation yet, but he primarily uses it for phase calibration. There's some more information in his documentation for vlfrx-tools, and I invite you to check that out. And it is possible for field strength and amplitude calibration as well. But for the signal analysis functions that Paul does, it's in vlfrx-tools. It doesn't seem to be very important.
Thank you.
Mm-hmm.
Dave New asks, is there any noticeable reception of passive key fob systems operating on either the 125 kilohertz or 18.2 kilohertz? He says those are B field systems, so in theory they shouldn't propagate very far.
Well, I believe that because those signals are usually so weak, you would have to be pretty close to the antenna to actually pick it up. That's the good thing about those sorts of things, is that if their transmitters are fairly low powered, then it's really not going to cause that much interference. I would imagine that would show up as pulses on the incoming stream. A big source of interference is it's an automated meter reading standard. It's abbreviated TWACS, TWACS, and that superimposes pulses onto the 60 hertz sine wave, and the high frequency components of those pulses generate a lot of noise, and they present problems to these sorts of systems. So that's unavoidable interference, because those are radiated on the power lines. But as long as the key fob is far away, there shouldn't be that much of a problem.
And John, N8UR, and Scotty were talking, wondering more about your clock requirements and what you need from the clock module and how we would get. So what frequency do you need, and how are they going to provide it? So maybe Scotty and John can jump in here for a minute.
Yeah, so we just need to know what frequency you're going to need, and generally it's preferable to get the frequency from a clock generator or a synthesizer rather than through an FPGA because of jitter issues. But
yeah,
go ahead.
Well, so the plan was for the GPSTO, since you mentioned that it had 4 programmable clock outputs. One of those would be used for the master clock of the ADD converter, and based on the channel configuration used, it would set the frequency. And from the looks of it, it looks like the maximum frequency is around 50 megahertz, but it really depends on how you configure the ADD converter. That's why I included that table in the presentation.
Right, and it looks like the range is 30 to 50 megahertz, so we just have to make sure the synthesizer can generate that. I think it can, John, right?
If we build with the synthesizer module, yeah, we can generate any of those frequencies without any problems. It's just the current design for the CKM doesn't have the synthesizer. Would have to be
Right.
the
Yeah.
synthesizer version, but with that, it'd be easy to generate those.
Well,
Right.
we could generate it in the FPGA if you're willing to tolerate the increased jitter performance that you're going to get from it. I don't know how critical that is for you at this frequency range.
Well, that would be when I'm actually testing this module. That would be something to investigate. I was also thinking about using. I remember reading or hearing somewhere that there were going to be lower cost clock modules based on some sort of a TXCO or other sorts of frequency sources. So I was thinking about using those also as an option if you don't want to do sudden ionospheric disturbance detection, where you don't really need that accurate of a or you don't really need a fairly jitter-free clock. So that's also an option too, either from the FPGA or
another option would be for you to synthesize a clock on board from a standard frequency that we give you. Say we were to pick 25 or 50 megahertz and say you always get that, and then you could go from there. Would that be an option?
Yeah.
So anyway, we need to talk offline about this, and I think Steve is ready to chime in here on the break time.
Thank you so much, Jonathan. It's been great having you.
Thank you.